For number 9, I am now given an algebraic equation that is not in the form some expression involving x and y is equal to a constant. So in particular, what I'm given in the textbook is z is natural log of x squared plus y squared. I'm supposed to think about the solution set to that algebraic equation. Now, this, of course, is the solution set to that algebraic equation. But I can rearrange the description of that solution set to look like the description of the level set of some function of 3 variables corresponding to 0. Right? So, you could think of this as a solution set to an algebraic equation. You could think of this as a level set of a function of 3 variables corresponding to 0. And of course, they're equal because the conditions are equivalent on the two of them. All right. So in this, I've decided to go back to talking about a function and the gradient of a function as our justification for doing what we're doing. I start out by saying, since the gradient of f is normal to the level sets of f, the plane tangent to this set, that set is equal to, well, this set is equal to that set. That is to say, okay, so I'm now going to give a description of that set, i.e. the level set of the function of 3 variables, f, x, y, z, is the natural log of x squared plus y squared minus z, corresponding to 0. Okay, now, the textbook then tells me that I'm not supposed to find it just, let's see, I'm not looking for the plane tangent to this level set at 3. No, that doesn't make sense. I need to find it at some point in the domain of f of x, y, z. Yeah, the function of 3 variables. And 1, 0, 0 is a point in that domain, and it's a point in the domain that is in this level set. Let's take a look at what happens if we substitute 1, 0, 0 into this expression. Do we get a true statement? Natural log of 1 squared plus 0 squared minus 0 is equal to 0. Natural log of 1 is 0. Indeed, this works. Okay. So that point is in this level set of that function. Then, we say that the normal vector dotted with xyz is equal to the normal vector dotted with the particular point in the plane, or rather the position vector of that point, and I've simply moved the normal vector, which is the gradient, dotted with the position vector 1, 0, 0 from over here to the other side, and then factored out gradient of f, and that leaves me with an x minus 1 yz. You should be getting used to this at this point. Of course, the reason I did this is because I didn't want to write out grad f twice. It just saved me a little bit of writing. Now, what remains to be done is to calculate the gradient of f and evaluate at 1, 0, 0, and then take the dot product. So let's see, the gradient of f, natural log of something is 1 over something. I could, let's see. For the first component of gradient f, I'm looking at the derivative of this with respect to x. So z is a constant. I see natural log. I want 1 over the argument of natural log 1 over x squared plus y squared times the derivative of what's inside with respect to x, and that'll give me a 2x. And then similarly, the derivative with respect to y. And then the derivative with respect to z, we'll see the natural log part, the natural log term here as a constant, so that'll vanish, and I have the derivative with respect to z of negative z, negative 1. And I need to evaluate that at 1, 0, 0. And then dot with x minus 1, y, z. Okay. So let's take a look at this. 2 times 1 over 1 squared plus 1, so that is a 1. That'll be a 0, so this is 1, 0, negative 1. Okay, I think I can just do that in my head. If this is going to be a 1, then I have 1 times x minus 1 for the dot product. And then I have, this was a 0, 0 times y. So 0 will not, so y will not appear. Well, I need not write y, rather. Minus 1 times z is equal to 0. Okay. Now, taking a look back, you may be perfectly happy with the wording, but I am not. The level sets of the function corresponding to at the point is. Now, is an equation? No, it is the solution set to. the algebraic equation in 3 variables you could also write if you wanted to specify, but I think we'll take the usual convention that if you only see 3 variables, there only are 3 variables.